So, as I told you before, this chapter, it's frozen. Yes. So let's start. So good morning, everybody. So as I told you before, this chapter is about digital transmission. The idea of the digital transmission, as I told you, if you have data, digital data like 1010 and so on, we're going to transfer this data as a digital signal or discrete signal this way, okay? For example, it can be something you will see right now, but it can be something like that, okay? 10110, whatever. So it's going to be, so the signal you are going to transmit digital. Is that okay? You're not going to transmit it analog. You're not going to convert it to analog, okay? So, and I told you before, this one is used in case the link you have is low pass filter, okay? And in this case, you use the whole channel. So use the whole bandwidth, use it for this transmission. So, and that's what we call digital to digital conversion. So digital to digital means, I think I have a figure here. As you see here, our data, the first digital is for data, the second digital for the signal, okay? So what we do here, we need to use encoder and we need to use decoder. What the encoder is going to do, the encoder is going to take digital data and then it's going to convert it to digital signal, okay? The decoder is going to do the opposite. It's going to convert the digital signal to digital data, okay? So before, we are going to teach different ideas for this encoding. How can we do encoding? But before I teach the different schemes for encoding, first we need to know how good encoder should look like. What good encoder should do, so that when every time I teach one scheme for encoding, you can judge, you can tell if this is a good, if it's a good approach or not. Okay, so the first of all, the first metric I'm going to use to tell if this is a good encoder or not is actually the bandwidth needed. And I told you last time, the bandwidth is, we're going to compute it using this formula. The bandwidth or the signal rate here is C. I told you C is constant, and most of the time C is going to be half, 1/2. N is the bit rate, and then 1/R. Okay. So what we're going to do for every scheme or for every encoding scheme, number one, we're going to calculate R. And then after we calculate R, we're going to calculate S, the signal rate or bandwidth, okay? So for sure, the smaller the bandwidth or the smaller the signal bit is going to be the better for sure. You got what I'm saying? So this is one way or one metric I'm going to use to compare the different metrics, compare the different encoding approaches together. So that's what we're going to do. Every time we're going to calculate R and then calculate S. The smaller this, for sure, is the better. So the question is now is what is S? How can you, what is R? How can you calculate R? So last time I told you R is actually, so if you see something like that, we have here data element. Data element means 1 bit. Okay. We have also signal element. So here we have this signal element here. Okay. So here you can see R is actually how many data element we have divided by signal element. So here is going to be 1 bit divided by 1 signal element. So in order to transfer 1 bit, I need 1 signal element here. So that's why R here is actually 1/1, which is 1. Let's look at this case, another case here. We have here 1 data element, which is 0, 1 data element, which is 0. But to transfer this data element, I need 2 segment element, as you see here, 2. That's why R here is half, okay? Let's look at this one here. Okay, let's look at this one first here. If you look at this one, here, this is again this different encoders. I'm showing you how can we calculate R. So here we have two elements, okay, and we have only one signal element. So for every signal element, we're gonna transfer two data elements. So this one actually is gonna be 2 divided by 1, which is 2. Okay, let's look at this one here. For example, this one is gonna be 4 divided by 3. Okay. So again, we're going to do that for every encoding scheme. We're going to calculate R. After we calculate R, we're going to calculate S. And the smaller the S is, the better for sure. Okay. But the question is that, so you can tell from here, if higher R is better or smaller R is better. Okay. The answer is the higher, as R is higher, for sure is going to be better. Why? Because I'm going to need a smaller amount of bandwidth from you, which is good. You got what I'm saying? Because if you look at the formula here, if you look at the formula here, so the higher R is better. Okay. So, and I think in the book, they have a very good analogy to what we are doing here. The analogy is, imagine every signal element is like a car. Imagine every bit like a passenger, okay? And we're gonna, so here, if you see what I want to say here, so here, I'm gonna use only 1 car to transfer 1 passenger. Here, I'm gonna use 1 car to transfer 2 passengers. So imagine every single element like a car, okay? So again, for every encoding scheme I'm gonna teach, the first thing we are gonna use to evaluate it is actually S, or the bandwidth, using R. There are other things also we can use. I started to explain them last time. So one of the things is DC component. Okay, for sure, if it does not have a DC component, it will be better. So I'm gonna explain what is this. Also, we have what we call baseline wandering. We have synchronization problem. If it doesn't have a synchronization problem, it's gonna be better. Complex. If it is not complex, it's gonna be better, and so on. Okay. So I'm gonna make a quick revision on the synchronization problem I explained last time. So the main idea here is that you have a sender and you have a receiver. Is that okay? So actually here, there should be, when you transmit, let me first tell you the correct way. And then after that, I'm going to tell you what happens if there is an error. The correct way is, if, for example, here, we have to use the same boundary. So we have to use the same boundary for the bits, okay? At the sender and at the receiver. So that if this one is high at the receiver, because it's the same boundary, okay? If it's the same boundary, so if you transmit 1, I will receive 1. If you transmit 0, you are going to transmit 0. Because we are using the same boundary here, okay? The same time frame. So this is how it should be. In reality, it's not going to be this case. It's not going to be like that, okay? What may happen in reality, maybe you are going to use this boundary as a sender, but at the receiver, this will be my boundary here. For sure, this is what we call lack of synchronization, okay? So we use different types here. Okay? And because of that, what's going to happen, you are going to transmit some data. I'm going to receive wrong data. And I have a very good, I have a very good example here to understand what I'm saying. So at the sender, this is the boundary at the sender here, okay? But at the receiver, this was the boundary at the receiver here, okay? So what happens, you transmitted 1011 0001, But what's going to happen? I'm going to receive a different data, because what's going to happen when you transmit this one here, as you see here, I'm going to interpret this one here, although you transmit only one bit, which is 1. But as a receiver, I'm going to interpret it because my boundary is here. I will think that you transmit 1 and 1. You got what I'm saying? Because we are not synchronized in time. In the time, we are not synchronized. You got what I'm saying? So if you transmit this data, because of this problem, you transmit only 1, but I should have really receive like 1 and 1. Okay, so there's something wrong here. Okay, that's what we call if there is lack of synchronization. Okay, so first of all, why we have this problem? Why not both of them are going to use exactly the same boundary? Because as I told you before, if you use electronic circuit here, that's exactly what we do at the sender and receiver. We use electronic circuit to generate a clock. We use also electronic signal to generate a clock. What happens, and this is something normal, this clock, it changes over the time, and that's normal. Why? Because you use capacitors, you use clock. All the capacitor and the clock are maybe impacted by temperature. So, but because of the temperature, because of the aging, as the capacitor get older, the value of the capacitor, because the capacitor has some chemical material inside. Okay, for sure, some of the capacitor have some chemical material. So over the years, the value of the capacitor will change. Okay, so anyway, that's what you should understand. Even if you do your best to have exactly the same clock, in reality, over the time it's going to be different. Okay, so we have different. So because of this, this is a very serious problem. If you transmit some data because we're not synchronized, I'm going to receive different data. Okay, so how can we solve this problem? Is this what we call synchronization problem or lack of synchronization? The answer is we need to do something we call self-synchronization. How can we do that? When you transmit this signal, you have to send something that should help the receiver to resynchronize, to correct himself or itself. Okay, so the receiver has to correct itself if something is wrong. You got what I'm saying? As you will see later, one of the ideas here is return to 0. Okay, so here, especially this problem, the self-synchronization problem, especially happens when, for example, if you have here, if you transmit 0, 0, 0, for example, and then 0, 0, 0 are going to transmit, for example, positive voltage for some time, or 0 voltage, okay? Or you transmit negative voltage for some time. So I'm going to lose synchronization, okay? So in order, as you will see later, the best way to solve the synchronization is transitions. If we have transitions, so if you make some transitions here, transitions this way, so if my clock is here, I can know if my boundary is here and there's transition here, I can know something is wrong, so I can shift this way, or I can shift this way to align. I need to align with the transition. Okay. So again, so if I give you, and that's what I'm going to do right now, if I give you an encoding scheme, and you want to tell is there a synchronization problem or not, what should you do? All what you have to do, you have to see when you transmit 0, 0, 0 or 1, 1, 1, 1, the voltage is going to be fixed or there are transitions. You got what I'm saying? If the voltage is fixed, so you have synchronization problem. If there are transitions, you don't have a synchronization problem. Is that okay? Okay. So that's what you're going to see right now. So you are going to see some encoding schemes have these problems. Other encoding schemes don't have this problem. Okay. I'm telling you, how can you judge if there is a problem or not? Okay. So here we have, if the voltage fixed 0, positive or negative for some time, is this for sure? This is not a good. This is not good for synchronization. Okay. The other thing here I want to teach is what we call. Let's go to base wandering. Okay. Also, what is base wandering? I'm going to tell you what is base wandering here. So again, I'm going to repeat it again because that's very important. If I give you encoding scheme and you want to know if there is synchronization problem or not, okay, see how it works and to try to see, is that possible if you transmit some numbers, whatever the number, it doesn't matter. It doesn't need to be 0, 0 or 1, 1. Whatever the number, is that possible that you are gonna the level, the voltage level are gonna be fixed for some time without transition? If the answer is yes, yes, you have synchronization problem. Because these transitions is going to help the receiver to resynchronize, to correct himself. Okay. So anyway, so this number one. Number two, still wandering. Okay, baseline wandering. So what baseline wandering means? Okay, so when you transmit a signal this way, for example, as a receiver, I need to decide once you transmit, I need to decide if this is high voltage or low voltage. Is this is 1 or 0, right? I need to decide if this is 1 or 0. Okay. So very simple way. So what should I do after as a receiver side, after I receive this signal and I want to know if this is 1 or 0? What should I do? What usually, for example, if we have here 0 volt and we have here, for example, 5 volt. Assume 5 volt is 1. Assume 0 volt is 0. For example, logic 0. So in this case, what usually we do, I can simply make what we call a baseline. This is a baseline. Okay. I can make something like a baseline. I put it in the middle here, for example, 2.5 volt. Okay. And then if the voltage I'm going to receive is more than 2.5, I will assume this is 1. If it is less than 2.5, I'm going to assume this is 0. Is that okay? So I have a baseline. If the voltage is more than baseline, it's 1. Less than baseline is 0. Is that okay? In reality, we can't do this way. Why you cannot do this way? Simply because the signal I'm going to receive is not going to look like this signal. Because of the noise. You got what I'm saying? If the signal is going to be something like that, okay, so I don't have any problem. I'm gonna compare the voltage I receive to 2.5. Above is 1, lower is 0. My life would be easy, but it's not like that. Because what happens because of noise, okay, what happens, maybe at some time, yeah, let me make a different color here, yeah. Yeah, maybe for some time you can find here the signal I'm going to receive, it will be something like that. You got what I'm saying? Or it's going to be up or it's going to be down. So the voltage may be up or down. You got what I'm saying? So having a fixed, this is a problem. Fixed baseline is not a good idea. Having a fixed baseline is not a good idea. So what is the other option? The other option, I can have like a variable baseline. Why it is variable? Because of the noise. The noise is random. The noise is variable. You got what I'm saying? So what do you mean by variable? All what I'm going to do is I'm going to calculate the average voltage I'm receiving. Okay? So I'm going to calculate the average. So here, so this one is going to be variable. Okay? Assuming most of the time you are going to transmit 1, 0, 1, 0. So let's see. So what we do here, I'm going to calculate the baseline is going to be variable because noise is going to change. You got what I'm saying? Variable means this is happening by calculating running average. Okay, so I'm going to calculate a running average. Okay, because most of the time the 1 has to be higher than a certain value. It doesn't need to be 2.5, maybe something else because of the noise. And also 0, logic 0 should be below a certain value. So I'm going to make it variable. Variable by running every time I receive a signal, I'm going to update the baseline. Okay. So let's look at the very, very good scenario and what is the bad scenario. The good scenario is, okay, look at the idea here. The good scenario is if you transmit, for example, 1, 0, 1, 0. So 1, 0, 1, 0. This is a perfect scenario. 1 and so on. Why this is a perfect scenario? Because what's going to happen is that here, okay, so what's going to happen is that because this is 1, here, for example, you have a baseline here. Because this is positive voltage, so the baseline is going to go up. And because it is 0, it's going to go down, go up, go down, go up, down. So it's going to, the baseline will be something like that. You get what I'm saying? Because 1 is positive, so it's going to go up, negative, down, 0, positive, 0, positive, 0. So when you calculate the average, it's going to be something like that, which is very close to the middle. You got what I'm saying? So this is a very good scenario. Okay? So here we don't have a problem. Everything is okay. However, so what is the problem? The problem can happen if the signal becomes something like, is gonna, for example, high for some time, like 1, 1, 1, 1, 1. If when I transmit 1, 1, 1, 1, the encoder is gonna say 5 volt, 5 volt, 5 volt, 5 volt, 5 volt. What's gonna happen here at the receiver side, this average value is gonna go high. You got what I'm saying? When the average value get high, so now errors are gonna start, because I told you anything that's above the baseline, okay, is 1. Anything below the baseline is 0. You got what I'm saying? It's the same thing if you transmit 0 for some time. If it is 0 volt, 0 volt, 0 volt, 0 volt, okay, what's gonna happen? This one is gonna go down here this way. Or if it is negative, okay. That's what we call baseline wandering. Baseline wandering. So I created a problem at the receiver. Okay. So if I give you an encoding scheme and you want to know if we have a baseline wandering problem or not, how can you know? Very simple. For any pattern, for any number, whatever 1 or 0 or any pattern, can I have 5 volt fixed this way for some time, or a certain voltage? It doesn't need to be 5 volt, positive or negative or 0. Do you have one voltage that's fixed this way all the time? If the answer is yes, so yes, you have baseline wandering. You got what I'm saying? By the way, this is the same thing for synchronization. Is that right? So again, when you design the encoding scheme, what is the worst? What is the bad? You should first, before I teach any encoding scheme, you have to first to learn what is good, what is bad, so that when I give you encoding scheme, it's going to be easy for you to tell if this is good one or bad one. Okay. So again, I'm going to say it again. If your encoding scheme is going to have certain voltage, 0 or positive or negative, doesn't matter. If this voltage is fixed for any pattern, of 1 and 0s, okay? If the voltage is fixed for some time, this is bad for synchronization. This is also bad for baseline wandering. Is that okay? For both of them. Okay, so what is the best way? The best way is to have transitions. And that's what you will see. This is the best way. So even if I transmit 1, 1, 1, 1, yes, the best way to have some kind of transition this way. Yes, this is the best way. If you have a transition this way, this is going to help synchronization. It's going to also help, or it's going to avoid a baseline wandering. Any questions? Okay. The last thing here also very important, we're going to use all the time to evaluate the different encoding schemes. Well, we call it DC component. Okay. Do you remember when I taught the time domain of frequency domain? I told you in the frequency domain, if you have DC this way, okay, and this DC is going to be in the frequency domain is going to be 0. Is going to be frequency. The frequency. What is the frequency? If you have a signal like this one, what is the frequency? Frequency is 0, right? And we call this one DC component. So if your signal, so if you have a composite signal, whatever how it looks like, so you have a composite signal, okay? And then the composite signal has, if you look here, it has 0, it has a component, it has some component here, not only at 0, but at a small frequency. It's also called DC component. So DC component means my signal has low frequency component, low frequency signals. Is that okay? Okay, that's okay. So what's the problem? So again, what I'm saying, if your signal, if you look at the frequency domain, if you at low frequency, if you see at low frequency here, this is the frequency domain. If you look at the low frequency and you see the amplitude at the low frequency is high, that means the signal has a DC component. Is that okay? Let's see another example. In another example, here, the signal does not have a DC component. What is this example? Yeah, for example, here, if this is a frequency domain, you have something like that. This is a frequency domain. Is there a DC component here? The answer is no, because I'm going to look at the small frequency here. The amplitude of the signal at the small frequency here, almost 0 or very small. So I don't have, so there is no DC component in the So there is no DC component in the signal. Is that okay? Yeah, that's what I'm going to say right now. Okay. So now, why DC component a problem? You are telling me if you have a good encoder, the good encoder should not have zero component. Should not have a zero component. Okay. So or sorry, DC component. Okay. Or zero volt, zero frequency. Okay. And again, it doesn't need to be zero. It means small voltages, 10 hertz, 3 hertz. We still will consider them like DC component. Okay. So why DC component is a problem? Why a good encoder should not have a DC component? What is the reason for that? The reason of that is, remember, my channel, the channel is actually has low pass filter effect. Also at the receiver side, we're gonna use low pass filter at the receiver side. Okay. So here we have low pass filter effect, and also we have here low pass filter. Okay. So as you know from the low pass filter, what happens is that this is, if it is ideal low pass filter, it has to be something like that. Okay. So it can pass all frequencies from 0 until F if it is ideal low pass filter. In reality, it's not like that. In reality, a low pass filter actually has something like that. Okay. Oh, sorry. I'm sorry. I think. Yeah, it has reality has something like that, and then goes this way. Okay, because this is a certain frequency, it cannot pass. So most of the low pass filter has some difficulty to pass or to accept the DC component, the low frequency. You got what I'm saying? So because of that, because of the channel is not going to allow the transmission of low frequencies, it's the same thing for the receiver. Good encoder should not have DC component. Okay. So now, number one, you should understand what I mean by DC component. Number two, you should understand why the encoding scheme should not have a DC component. More importantly, how I can tell if the encoder has a DC component or not. How I can tell? Number one, very simple. You can look at the frequency domain. If the frequency domain something like that, and if you look here and you find the frequency is too high, in this case, it has DC component. Is that okay? But if something like that, so here it does not have DC component. So you can tell from the frequency domain of the signal. Okay. Okay. So, but why we may have DC component? I'm going to tell you why. Again, the problem is that if for any patterns, either 1 0 0 0 1 1 1, whatever the pattern is, for any pattern, if the voltage of the signal is going to be high voltage for some time or low voltage for some time, this is going to create DC component. Zero is not going to create, so we don't have a problem with zero. Zero is not going to create DC component. Why? Because zero, here the amplitude is going to be zero. Amplitude is zero. It doesn't matter if you pass it or not. It doesn't matter because the amplitude is zero. You got what I'm saying? So I'm going to tell you the conclusion because that's what I'm going to use right now. Number one, for any encoding scheme I'm going to teach. Okay. Number one, you have to calculate the bandwidth or the signal rate, which is equal C times N times 1 over R. Okay. So C is half. That's easy. R, you have to see the ratio, how many data elements, ones or zeros, divided by signal elements. That's what I'm going to do now. For every scheme, I'm going to do that. Okay. So this is number one. The higher S is going to be better. That's number one. Number two, for synchronization, if you look at the voltage, for any pattern, can the voltage be zero for some fixed zero for some time, or fixed positive for some time, or fixed negative for some time? If this is the case, yes, we have a synchronization problem. We need to introduce transitions to help the receiver to resynchronize. Is that okay? Same thing for baseline wandering. It's the same thing. If it has a zero or negative or positive this way, okay? It's fixed for some time. But for DC component, Only problem happens when you have positive or negative. We don't have problem with zero. You get what I'm saying? So that's what you will see right now. So let's start one by one. So here, I'm going to teach line coding, which is different types of encoding schemes. So I'm going to start with unipolar. Maybe you're already familiar with some of them. So I'm going to teach unipolar, polar, bipolar, multi-level, multi-transfer. So let's start with the first one, which is a very easy one, unipolar. So the unipolar should work this way. Again, remember, any encoding scheme A is given binary data, how I create a signal, voltage. This is how it is, okay? So here, this is a very simple way. We call it non-return to zero. So what happens here is that this is very simple way. What happens is that every time you have one, I'm going to make it V, voltage V, okay? Logic zero, I'm going to make it zero, okay? Voltage zero, okay? By the way, it can, so here I'm going to use two different voltages, one for one, and one for zero. And one of them is zero, and the other one can be good or can be negative. You get what I'm saying? So I use zero, and then either positive or negative. Doesn't matter. Here I give you example for positive, but also it can be for negative as well. So let's start to think about everything I explained right now. Okay, let's start about R. What is R? Okay, so this is the signal element. Here we transmit only one bit for one signal element. So it should be 1/1, which is 1. Okay, so R is 1. You transmit one bit in every one signal element. Okay, and now you plug in this formula, you find that S is equal N divided by 2. Okay, this is the first thing. Is that good or bad? This is wonderful. This is great. Why? Because this is the best thing we can do in the case of two-level encoder. Okay, so the best thing we can do when it is the bandwidth required is actually N divided by 2, or the bit rate is double the bandwidth. So this is perfect. That's good. I can say this is great. That's good. Okay, for 2. Okay, let's think about the other things. So, for example, if you think about here, if you think about synchronization, ask yourself, can the voltage be fixed 0 or positive or negative for some time? The answer for sure, yes, for sure. If we have pattern 1, 1, 1, 1, 1, it's going to be positive all the time for some time. This is so you have synchronization problem. If it is 0, we have pattern 0, 0, 0. Also, we have a synchronization problem. Is that okay? Yeah. So this is very simple. We have synchronization, lack of synchronization. Okay. Same thing for wandering. Okay. Baseline wandering. Okay. For baseline wandering, same thing. Can it be fixed positive or at 0? The answer for sure is yes. So this is bad for sure. This is bad here. This is bad. Do we have DC component? I told you in DC component, I don't care about the 0 voltage. I care about positive or negative. Can the voltage be positive for some time or negative for some time? For sure, the answer is yes. So anyway, this is a very simple encoder. We can achieve the best. This one can achieve the best bandwidth. Okay, nothing else. It cannot achieve anything else. Okay, it's for sure. It's also simple one. But for sure, we have a problem with baseline wandering DC component and also lack of synchronization. Any questions? Okay. So the second one, we call it polar. In case of polar, here, as we see, we have two versions of this one. Again, I'm going to repeat the same thing again. Number one, I'm going to tell you, for every encoder, number one, how it works. Number two, calculate the bandwidth. Number 3, do we have a DC component or not? Do we have synchronization problem or not? Okay, baseline wandering or not? That's it. And then based on that, I see if it is good or bad. Okay. So for example, here, so as you see here, this one is exactly similar to the previous one, but instead of using positive, here what we did before, it was 0 volt, and then we can positive or negative, one of them. Okay. But here, no, we don't have 0 volt. So here, we have positive and negative, okay, as we see here. So 0 is positive volt, 1 is negative volt, positive, and so on, okay? This is one version. We call it a non-return to 0 level. We call it level because actually the binary information can be determined by the level. So the value of the level can tell me what is the binary information. Okay. The other one is called invert. Invert. So invert, it works. So in case of invert, the binary information is stored actually here in the transition. Is there a transition or not? It's not stored in the level. It's not stored in the voltage level. For example, that's what I'm telling you here. If there is no inversion, so next bit is 0. So for example, is here, this is, and if there is inversion, so it is 1. So now 0 or 1 are not going to be positive voltage or negative voltage. No, it's not related to the voltage. It's going to be related to, is there inversion or not? Okay. If there is an inversion, so that means it is 1. If no inversion, so it's 0. So for example, look here, this is high, and there is inversion here for sure. Because this inversion, so this one has to be 1. Is that okay? Here, there is no inversion. So this one actually 0. Okay. Now, there is no inversion. So this one related to 0. Okay. Now, there is inversion. So this one is 1. There is inversion. It is 1. Okay. There is inversion is 1. No inversion is 0. And so on. You can see it. Again, what? Okay. In exams, how you are going to discuss in this? Number one, you should understand how it works, right? For example, I can give you any number, 1 0 is different from this number. I can give you any number, and then I'm going to ask you to do this signal. If you know how it works, you should be able to do that. This is number one. Number two, for sure, you should understand the advantages and disadvantages of each one. Okay, so let's look at this one, how it is good or bad. Okay, by the way, there is something interesting here. What is the interesting? Look at the one. Everyone here is going to be toggle. So if you have different from what I did before, so if you have 1 1 1 1 1 1, I'm not going to have fixed voltage because I told you fixed voltage is bad. So 1 1 1 1 is going to make toggle 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 toggle, which is good. You can. What is that?
0 0.
Yeah, that's why we can fix the problem only 50% of the time when we have 1 1 1. You are right. Yeah, but if you look at 0 0, 0 0 is going to be no change, no change, no change. You got what I'm saying? So it's going to be fixed. It can be fixed here, or it can be fixed positive or negative. Doesn't matter, positive or negative, but it still has the same problem. So let's. So any question about how it works before I move to the advantages and disadvantages of this one? Which one? Here, this one? This one here? No, here always 0 is positive volt, 1 is negative volt all the time. You got what I'm saying? Because we have two versions of them. This is level, the second one is inversion. For level, for 0 is going to be positive all the time, for 1 is going to be negative all the time. Is that okay? Yeah. So let's look at number one. What is R? Can you calculate R? What is R? R is here. Okay. So you can see every signal element, we have only one data element. So 1 by 1 divided by 1. We have only one bit. Every signal, one bit, one. Okay. So it's going to be 1. So R is 1. R is 1. So the bandwidth is N divided by 2. N divided by 2. That's very good. This is the best I can get out of it. I told you before, the best you can get is actually N divided by 2. Okay. So now let's look at the other things like synchronization. Like synchronization, for sure, we have here. For this one, we didn't fix anything here. So still here we have synchronization problem because we can have a fixed voltage. Okay. Also, we have DC wandering. Also, we have DC component. So this one is not. Maybe here I did something interesting here. What I did here interesting is, as I have just explained right now, when you have 1 1 1 1, so this 1 1 1 is going to make toggle. Okay, so actually here, in case of 1, we don't have a problem. The problem is going to be in 0. So I was able to solve the problem of the synchronization and also synchronization and DC wandering only 50% of the time. 50% of that. So also, if you look, I told you, if you look at the frequency domain here, if you look at the low frequency in this point, you can see you can see we have DC component. It's very obvious. We have DC. Okay. Yeah, sure. No, this is two different approaches under non-returning to zero. So we have two different approaches. Okay, one of them, I'm gonna store the data using the level. That's why we call it level. The second one, I'm gonna store the data if there is inversion or no inversion. Okay. Okay. So again, also this one suffers. So again, let me, the bandwidth is good. This one can solve 50% of the time. There is something also here you need to think about. What about error propagation? Error propagation. You know what I mean by error propagation? Error propagation means like domino effect. Or if you have error having one time, this is gonna create 3-4 errors next to it. Okay, this is error propagation. For sure, there is error propagation here. Why? Because this one here, if there is one error here happens, okay, it's gonna propagate because here if there is this one actually should be there is inversion, okay, because it is one. Because this one is one, there is inversion, okay. Imagine this one was wrong. Imagine the signal will be completely different. You get what I'm saying? So it's gonna make error propagation. So if only one bit is wrong, so here instead of, because this one is one, so I'm gonna invert it. Okay, imagine I'm gonna receive it mistake, okay, or it has it was wrong. Okay, so that means I'm gonna make it this one. I'm gonna assume this one is 0, so I'm gonna make it fixed. After that, you can see the error is gonna propagate. Okay. Any questions? Okay, great. So here I give you just very simple example. Just here I'm telling you, in case of non-return to zero inversion, our data, by the way, this is not 10, this is only 1, okay? So here I'm asking you to calculate what is the signal rate, okay, and the minimum bandwidth needed, okay? So actually the minimum bandwidth is equal to the signal rate, minimum. You can have more, but that's the minimum bandwidth you have, okay? So as I told you in this case, the signal rate is n divided by 2. And that's good, by the way. I told you this is the best we can do. N divided by 2, okay? So it's n divided by 2. So all what you have to do, just to divide this one is 1 megabit per second divided by 2. I'm gonna get 500K baud. And this is the signal rate, which is, so the minimum bandwidth I'm gonna get is 500 kilohertz. So you can see here, yes, they are equal, but here we use different units. Here for bandwidth, we use hertz, okay, or kilohertz, but for the signal rate, we use baud, kilobaud, okay? Let's move to the next one, which is polar return to zero, okay? So this one, again, polar, when you see polar means we are using positive, negative, 0, 3 voltages, positive, negative, 0. Return to 0, you can tell from the English name, return to 0, because if you see here, for every bit, what's going to happen in the middle, almost in the middle of every bit, we return to 0, as you see here. Here, we return to 0. In the middle of every bit, we go to 0. In the middle of every bit, we go to 0. In the middle of every bit, we go to 0. You see? Okay? But why? Why you return it to 0? And what is the cost for that? We return to 0, this is good for synchronization. Because if I lose synchronization, I'm expecting when you transmit a signal, I have to see positive or negative and then 0. Here, negative, 0, positive, 0, negative, 0, negative, 0, and so on. Okay? So always I'm expecting to see positive or negative, and then 0. Because of this 0, it's going to help me to synchronize. Okay? That's good, but we have to pay the price for that. Nothing is for free. We have to pay the price. So what was the price? The price was R now is half. Okay? That means I have to use 2 cars. I have to use 2 cars to transfer 1 passenger. And that's exactly what I did. Because this is 1 signal element and second signal element, and then here is so in order to transmit 1 bit, I need 2 signal elements. Is that okay? So this was the cost. Okay. What is that? We're not gonna talk. We're gonna talk about DC now. Okay, but let me go through them one by one. Number one, the bandwidth. So this one very bad. It's bad regarding bandwidth because this one actually needs double the bandwidth. The bandwidth here was n divided by 2, but now it is n. So we need double the bandwidth, which is bad. This is number one. Okay. Number two, synchronization. I'm happy for synchronization. Synchronization is very happy. Okay, very good synchronization because we always go to 0, but for sure we pay the price for that. DC component. Again, if you just look at the frequency domain here, you can see any DC component? No, we don't have DC component. Why we don't have DC component? Because it's not going to happen to have one fixed voltage all the time. Why? Because we always go to 0. You got it? So we're not gonna have negative. We're not gonna have positive. We're not gonna have that because all negative 0, positive 0, negative 0. So always return to 0. So DC component is good. We are good about DC component. Same thing for wandering. Can we have a baseline wandering? Can we have positive, fixed positive, or fixed negative, or fixed 0? No, we can't. So it's good. So it looks like everything is good except the most important thing, which is the bandwidth. You got what I'm saying? So this one is really everything is good except we need double the bandwidth. That's why. Okay, that's why we're not gonna. Usually we don't use it. Okay, because it needs too much bandwidth. Any questions? Okay, let's move to the next one, which we call bipolar biphase. So here for polar, I explained 3 different approaches for polar. So here for polar, I explained non-return to 0, okay, and I explained here 2, level and inversion, okay, return to 0, and now I'm gonna explain biphase and Manchester and the differential Manchester. I understand in network 1 you already had some idea about Manchester and differential Manchester. Number one, again I'm gonna repeat the same thing. Number one, how it is different, how it works. And then I'm going to compare everything I explained. So let's see how it works. For Manchester, the way Manchester works is, as you see here, every time we have 0, 0 is going to be signal like this one here. 1 is going to be negative and then positive, as you see here. So here, this is 0, always positive, then negative. 1, negative, and then positive. 0, positive, negative, and so on. If you do it this way. Is that okay? Now, for differential Manchester, here, we're gonna use the idea of inversion. So here, the data, the bits are not gonna be stored in the level. But so here, if I want to move to 0, it should be positive pole, negative pole. Is that okay? But here, then the inverter. Is it inverter or not? Okay. So here, always is still always we have positive and negative. So in every bit duration, we have here positive and negative. Some positive and negative. Always. But what happens is that because in case of 1, no inversion. So here, because this one is 1, no inversion here. So no inversion means this one is high, so this one will be high. But always we are going to go to 0. Always. Okay. Now, because this one is 0, so I'm going to do inversion. So I'm going to do inversion this way. Inversion means I'm going to start from the beginning will be different. No inversion means beginning, but always have to switch. Always have to switch. But this one is positive, no inversion, so I'm going to positive. But here, because this one is negative, there is inversion, so I'm going to start with positive. Okay? So I'm going to do it this way. Okay. Let's start again, compare different things together. Number one, what about the bandwidth? Still, the bandwidth is bad. Okay. It's double the bandwidth we got before. Why? Because look at R. R is bad. I need 2 signal, and I need 2 signal elements. I need 2 cars to transfer 1 passenger. You got what I'm saying? You can think about signal element like a car. Car is carrying bits. They are carrying bits. Okay. So here I need 2 to carry only 1 bit. Okay. That's why this is bad. Now let's look at other things. Number one, for example, here, if you look at DC component, you can tell from here there is no DC component here. But again, because there is no way we can get positive voltage fixed or negative voltage fixed, because we always, as you see here, we always half of the time high, always. half of the time high, half the time low, half the time high, half the time low. So you're not going to have positive all the time. So same thing for synchronization is good. Okay, so synchronization is good. Baseline wandering is good. DC component also is good. Okay. Here, the transceiver here. Transceiver means sender and receiver. When I say transceiver, it means sender and receiver. So sender and receiver are simple here, comparing to return to zero. Here, because I use only 2 voltages. So there is one important thing you should understand. The more levels you are using, the more complex the hardware should be. You got what I'm saying? Here, because I'm using 3 levels, this is the bad thing about this one. I'm using 3 levels. That means I should, because of using 3 levels, so this one is more complex than this one. Okay, so this one is simple. So everything looks okay again, but the most important thing is bad. The band, I need double the bandwidth. You get what I'm saying? So still, this is an issue here. So again, I need double the bandwidth. This is a problem. So I'm gonna work on this problem, and we try to improve it in next time. Okay. So I think we can take that case now. Five, 4, 9, 6. 5, 4, 9, 6. اوكي ماشي. يعني take some time يعني. ها؟ ممكن بعد الليكشر التاني. بالتالي يعني لحد الساعة كام؟ بعد 11. طيب ممكن تبعت لي ايميل، ممكن نتكلم في التليفون مثلا. افضل. Yes. What is that? Hey, come here. What's your name? Can you come?